So till now we have seen how to construct the Bode plot. Now to the application. What is it that we want from the Bode plot? We want to find out the stability of that particular system. So stability from Bode plot. Often what happens is we get the Bode plot instead of the transfer function. Okay. So directly from the Bode plot you can find out the stability irrespective of what the actual transfer function is. So let us take an example. What you will need is the magnitude as well as the Bode plots. Okay. So usually the phase is negative. So I am taking at the below this omega axis. Okay. Now let us say the magnitude, this is just for the sake of an example. So let us say the magnitude is something like this, and phase you can also take something like this. Now we will mark this as 0 dB, and somewhere here let us take this to be minus 180 degrees. For these functions we will try to find the gain margin as well as the phase margin. So the very first step we will take the gain margin. How to find the gain margin? So gain margin corresponds to what? The frequency at which the phase crosses 180 degrees. What is that frequency? The phase crossover frequency. This will be the phase crossover frequency, right? So you can note it down here, phase crossover frequency. Now what you will do is, for the same frequency you will draw onto the magnitude plot. So this is the magnitude at omega p, that is the phase crossover frequency. Now you have to find the corresponding magnitude here. Let us say this magnitude is x. Then what will be the gain margin? This is going to be minus 20 log x, right? This is as per the formula that we have already defined. What is x? This is nothing but the magnitude at the phase crossover frequency, right? So minus 20 log x, just that you are finding this magnitude with the help of the Bode plot instead of from the transfer function. Okay. So we know that for system to be stable, so you can write this here, Gm is equal to minus 20 log x. So we know that for system to be stable, the condition on the gain margin is that it should be greater than 0. So that means minus 20 log x should be greater than 0, meaning that the gain should be less than 0 or negative. Only then will the system be stable. So here if you can see, x is positive because 0 dB is here. So this, since the gain is positive, minus of that gain is going to be negative, meaning we have a negative gain margin, meaning that this system is unstable. Okay, so this is how you will get the stability information from the Bode plot. Similarly, you can find out the phase margin, right? This is also in the same procedure. So we will take the same function and we will see how to do this. Okay, so this was the function, and once again we will take minus 180 to be somewhere here. Now what do we need for phase margin? We will need the gain crossover frequency. That means where is the magnitude crossing 0 dB. So this is going to be the gain crossover frequency omega g. Okay. Now from here you will draw onto the phase plot. From here you can get the corresponding phase, right? So let us say this is going to be, let us say some y. Then what will be the phase margin? The phase margin Pm is going to be the phase at that point plus 180 degrees. Okay, so this is also directly from the formula that we have already discussed. Okay, so once again, if the system is stable, then what is the condition? Condition for stability with respect to the phase margin. This is what? It should be greater than 0. That means y plus 180 should be greater than 0. So only when y is greater than minus 180 degrees will the system be stable. But here y is less than minus 180 degrees. So this system is unstable. The phase margin for this particular system is negative. Okay, so both the gain margin as well as the phase margin has come out negative. So the system is completely unstable. This is how from the Bode plot you can find out the stability of that system.